All right. Okay, so the last time we actually stopped at motion control, and we will actually eventually move into force control as well in this course. So this is lecture 16, and please take note of what is going to come out on Blackboard. There will be details about your midterm test. Okay. Right, so the motion feedback control and linear system was what we have done for the last 3 lectures, and we actually covered including the modeling and control of second order system. So that was a very quick revision. Just a very quick check that you're able to see my screen and hear what I'm saying clearly. If so, just type something on the chat. Okay, yeah, thanks for. All right, so we were going to look at some non-linear systems as well before we move on to control. But today we will wrap up on our second order system and relate it to our independent joint control. So we look at the various components from actuators, sensors, as well as this transmission mechanism, things like our gearbox, etc. That was what we have done last week. And last lecture, we look at this modeling of second order system. And today we're going to bring them together to combine them so that you have a clearer picture of what is it about when we are doing individual independent joint control. Okay, so we will start off looking at this single joint control with control law partitioning. So that was what we have done in our last lecture, right? Control this control law partitioning. So last lecture we actually did this. Okay. And single joint control, we did it last week. So have a quick recap if you're not able to recall any of this, right? And finally, we will move on to non-linearity and computer taught control. All right. Okay, so last lecture, we did very much revisional stuff, modeling and control. So for most of you, you will have already taken classes on control theory as well as control system. So this should not be something unfamiliar to you. And you should also be comfortable with modeling the dynamic system that we are trying to control, or in this case, a plant of interest, okay, in the control terminology. Right. So starting off from second order system, right? We assume that we are able to say get information about x dot and x. That is actually your state, right? This is kind of like the state of your system. Okay, hang on. Let me end this for a while. Some problem with the slides. Okay. So remember that what we are trying to do here, okay, say we have a system, so we know the dynamics, or perhaps we do not know the dynamics of this system, but it is a dynamic system. And so we want to know what kind of input to send in so that we can achieve a desired outcome. And so in this case, eventually we design a controller. Okay, so these are your control gain. Control gains. All right. So from here, you can now change the system. Initially, you have something like this. Maybe I should. I will use a little bit of control terminology, the plant dynamic. Okay. So now, after doing a feedback control, okay, so this is now your closed loop system. Okay. And so with that, you have your closed loop stiffness, and this V prime here, okay, your closed loop damping. All right. And so that was one way that we can do it. We can assign something Kp and Kv. Okay, in this case, we can assign Kp and Kv, right? Let's see. And this, in a way, is like a black box. Okay. So at this point of time, we can treat this as a black box and assign Kp and Kv. So there is another way where we can make use of this control law partitioning. Maybe I will remove my screen is getting in the way. All right. Okay, now it might be better. I can write on screen. All right, so this is a case, say when we know our parameters, system parameters, we know B and K in this case. All right, we can actually separate our system into a model-based portion and a servo portion. All right. So the servo portion, you can come out with a servo law, which is very much the same as what we have done earlier on. So remember, previously, okay, I should actually use the same color here, right? Previously, this is our system. Okay, previously this was our system. And now this entire thing becomes what is inside here. Okay? So this entire thing, the entire thing is here. Okay, this was what we had previously. And we can put in M, B, and K. In this case, we have M, K. Okay. And knowing that, now we assign KP and KV. And now our closed loop system can be represented in a neater way. Okay. So this is how we do control law partitioning. So how useful this thing is may not be obvious at this point of time. As we move on, you will see that it actually helps when we are doing non-linearity and later on force control. Okay, and two other things that we did was trajectory following. Okay, we look at how we can specify certain desired position so that we can make sure that the robot is at the right place at the right time. Okay. At this point of time, path versus trajectory, just bear in mind there's actually a very big difference. Okay, path versus trajectory. But later on, when we do path planning, we will go into this deeper. And we realize that in the event of disturbance, when there are disturbance, okay, in order to reject disturbance, just our K, P, and KV would not be sufficient. Right? K, P, K, P, not enough. Okay, we need to put in Ki. Okay, so this entire thing gives us Pi. So that's the idea behind it. Okay. If you recall, right, if this is without disturbance, we just want to have a desired position. Okay. So this is right. We want to have desired xd, x dot d, or x double dot d. That is your displacement, speed, and acceleration. So we can now specify a desired so-called trajectory, and having that trajectory pass into our system, and the controller will come up with the right input to send into our system eventually, right? So eventually we will be able to have something that is sent into the system. But this, of course, will be fine if we are doing trajectory tracking without disturbance. So say in a case where we have disturbance, right now we have disturbance. Okay. So this is disturbance. Okay. In order to reject this, we realize that if we use just KP and KV, eventually we will end up with having this if our error derivative equal to 0. If this is equal to 0, this double dot is equal to 0 as well. Okay. So that is not going to be enough, even if our KP is very large, because there will always be an error. this is always greater than 0. Right? Even if we have a very large KP, you will have you will still have the some small value, which is what we call steady state error. All right. So we actually need this PID. We need to put in this KI, right? Where you integrate the error. Okay. KI integrate your error. Okay, so this thing will be feedback. I mean, this will actually be fed into the system. All right, error will be feedback and then integrated, multiplied by KI and fed into the system. So that is how this thing works. Right? So how is it related to our joint control? So remember that when we talk about having this robot, okay, this is going to be assuming that we have a robot. Okay, so each of them will have a joint. Okay, I mean, each of the link will be connected by to the previous link by a joint, and so you will have out here, and the joint will have this motion. So, and so our idea here is to control this individually, so that eventually we will be controlling this thing. All right. So that is the idea. Okay. And we need to understand the components and the mechanism when we talk about this. Okay. So how do we actually model the resultant system as a second order linear system, or actually as a dynamic system mathematically? We're going to combine the dynamics of this electromechanical system. And this is what we have actually seen last week, okay, when we look at this electromechanical system. All right. So in this case, okay, this will be a case where we have direct drive. Okay, so this is so that means there's no gear ratio, or rather gear ratio is equal to 1. Okay, remember okay, so your gear ratio is equal to 1 in this case. And then you work out your system using the physical law. You know that the torque of the motor is kind of like proportional to the armature current in this model, this armature DC motor. And there will be a back EMF, okay, that resists the motion. Okay, so if you have a motor spinning at theta dot m, you're going to have a back EMF, okay, that is proportional to this motion, but in opposite direction. All right, it has to be in opposite direction. Okay, so that it's dissipating energy. All right. So from Kirchhoff's law, you can set out the governing equation or your dynamic equation, okay, for the circuit, and then you substitute the value in, right? You substitute the value in to get what you have, right? And on the other side, you use Newton-Euler equation as well, okay? So you also set up this dynamic equation here, okay? Okay. So you have two dynamic equation, right? And this part you do the same thing. You substitute what you have here, okay, to establish your equation. All right. So that allows you to model this your single joint dynamic system. Okay, but the idea is to be able to control it. Of course, before that, if gear ratio is not equal to 1, we actually have a transmission mechanism, say a, a pair of gear that is attached, one to the input and the other one to the output shaft. Okay, so now we need to consider the gear ratio. Okay, so this is gear ratio. All right. So when we have the gear ratio, of course you can do a few things. We actually work out how it is related, your velocity and your torque. Okay, when you have a gear ratio that is greater than 1, it's going to reduce your speed and increase your torque. All right, and vice versa. So if your gear ratio is smaller than 1, you will have higher speed at the output side but lower torque. And so if we work out this from this model again, okay, so for those who forgot about this, okay, you can actually get a very quick review, but I'm not going to go through the detail. So basically, if you work out a model, okay, you're going to relate the torque of the motor, right, to the motion, which is the angular displacement, angular velocity, and angular acceleration of your shaft, motor shaft, as well as the output shaft. Okay, so this side here is the output. Yeah, here's it. Okay, side is your motor and your input. So we can rearrange it to kind of make the torque, okay, the torque as the subject of formula, and you will have effective inertia. That is a combination of the motor inertia and the load inertia. Okay, maybe I should use a more intuitive terminology. Okay, let me just this part here is the load. Okay. All right. So now we have this dynamic equation. So it's kind of like a governing equation. This is your governing equation. And so with that, you can also work out your control law, right? We can actually try out this, okay? So now that we have, let me maybe open up something. So now let's start with something easy to look at. So say for example, this time round, there are a few ways of seeing the dynamics. So starting from the easiest one, if we are looking at the direct loading, where our gear ratio equal to 1, okay? And just now we actually work out from the Newton Euler formula, we can have something like this, right? Okay, so this is what we have worked out earlier on. Okay, so if we rearrange it, okay, say for example, we make this a subject of formula. And we can actually put in the servo law. All right. So this is when we put in the servo law. And if you, so maybe this is not that. Let's not skip this, but let's continue putting it this way. Okay, so let's take this thing as the force that we have earlier on F, and then we set out this servo law. There's a minus sign. Okay, it should look something like this, right? And so this side here is of course B theta dot and I double dot can be equal to KP. It can look something like this. And so now our effective closed loop will have something like this. Okay. Of course, we are not saying that this is this is the best way of implementing the control, but this is one example that you can relate it. So earlier on, what we did for this is having this system, right? And this is a dynamic system where we send in, say, the certain torque. In this case, the torque of the motor, for example, and we're going to have the state, which is theta and, oops, I guess it's theta dot. Then I have theta dot and theta double dot, right? And now we want to feedback this to the system, okay? And we can really send in something. and we can have this controller AV. All right. So this is the loading part. Okay. So this could be one example. Of course, if you want to apply the control law partitioning, okay, we have to separate it into this model base. Servo. Okay. So we have the model base and the servo portion, right? So how we do that is that we make this right, something like this. Okay. And now our previous system we saw earlier on, okay, which looks something like this. Okay, maybe let me go back to the previous. Okay. So now this time around, what we do is our system, we will have information about, say, the B and I. Okay. So in this equation, okay, let's say we have the information of our B and I. Okay, let's say we know about B and we know about I. Right? So we can actually write this down. So we have our ether dot ether double dot. All right, the same thing. This is after we send in the input. Okay. Okay. As something like this. And so this part is what we know and put into the system. Okay. So previously, what happened is that we know that inside there is a dynamic system inside that will be doing this something like this, right? Let me see if it's, yeah, this should be correct. Okay. Yeah, so it could be something like this. And now if we do the partitioning, we can have if we let alpha equal to 1, in this case, we let this equal to 1, and what is coming out, this power load is actually alpha f prime, right? Because you have f prime being sending. Okay. Okay, let me maybe arrange this. Okay. And so our model base we can write it down. But this time around, let's bring our tau L to the other side so that we make this tau M the subject of formula. Okay. And so from here, of course, we know that this is really F. Right? So from here, we can actually substitute what was on top. Okay. Maybe to avoid confusion, let's put it in the same. Okay. All right. So now we can have the servo part. Okay. So this is the servo part. Maybe let me. Right. And we can now write. Okay. Which means that this is a bit too big. I can't draw my servo part. Give me a second. So the same thing, you should have AV and AP. That is this KV should be connected to this. Yeah, maybe I will just clarify by drawing one more. So it should kind of look something like this. Okay. I go in with BM, okay, and now you know B and BI, okay. Of course, this is from here to here, it's from here to here, right? Okay. So what is going to come out from here will be B dot, and this will be BI double dot. All right. And this part here is going to be our L. Okay, which is also like because if we have alpha here, and in this case we can put alpha as 1, right? So that this part here f prime, okay, that we're going to send in is also TL. All right. So this part here is the model base portion. Okay. So now we are looking at model base. I mean, all right. And then we can put in our this servo. Okay. Servo will have KV and KP. Right. Have our KP and KV that is connected, okay, to this. Let me see, KV, KP. Right. So your servo. Okay, so it should look something like this. All right. Okay, so this is, of course, this may not be the best control design, okay, but it is just to show you the example of how we model the system, and then we come out with a control scheme to accomplish the desired outcome that we want. All right, later on we can put in trajectory following, just like how we do earlier on. Okay, remember previously when we do this trajectory following. Okay, when you have a desired path, okay, when you kind of have this desired x d, x dot d, and x double dot d, okay, you can send them in minus by the actual outcome to produce the error. Okay, so this is the different when you are doing trajectory following, because you are sending in desired position. So just now what we have been doing is just position regulation. So we just want to keep it at one single position. Just like a spring, you want it to be at an equilibrium point. Okay, even if you don't do any external force, you don't have any control, it will eventually go to the equilibrium point. Okay, but you want to be able to control the damping ratio. You want to be able to control a few time response performance, like your settling time, your overshoot, okay, and things like that. Right, so these are something that will help you if you design this control system, be able to specify the system response performance. Okay. And of course, just to remind you that most of the time, for those who are working on robotics project, you will probably know that you don't really need to go down to the lower level, okay, the low level end of your control pipe to deal with all this, because a lot of time you actually have a integrated motor and sometimes an integrated servo motor, which will do all the closed loop control for you. So what you need to specify is usually only the speed or the position. Okay, so in case those of you who are working on practical project, you kind of want to understand what is really happening underneath the hood. All right, so this is really the entire control design approach. Okay, so from here, remember we actually have so if you look at this equation here, okay, you want to see what happens if this gear ratio get very, very large. All right, a few things. In the case of this motor side, of course, if you have very large ether here, okay, so this term, this two terms here will eventually be insignificant. Okay. If ether is a lot larger than 1. All right, so your I and B will be insignificant. I mean, this terms. Okay, so if you look at this part, okay, it will means that your motor side will be dominating. Okay. Okay, so the motor side will be dominating in this case. So that is why a lot of time we can assume the simplicity of this model here. And if you remember previously, we talked about which one is better for open loop control and which one is better for this closed loop control. And if we look at a gear ratio that is very high, okay, like in this case, this is very high, much larger than 1. Okay, your motor side will actually be the dominating one. So external force is not going to influence too much. And so most likely when you send certain command to ask a motor to move whatever displacement is going to be done more accurately. Okay, so the external disturbance will have less influence on it. And in such case, you don't actually need to do a closed loop as urgently as in the case of this A here. Okay. If you don't have, in this case, most likely you won't have very high ether, or sometimes gear ratio might be approximately equal to 1. Okay, in this case. Okay, so that is just a practical issue to let you know. So there are a few different robot scheme. We have earlier on looked at joint, independent joint. It's really joint control. Okay, so there are also things like Cartesian space. All right. So Cartesian space control is actually, just by looking at the name, you know that it's based on the task space. Okay, so it's actually task in the task space, meaning say X, Y, Z. Okay, and joint space is Q1 all the way to Qn. So this was what we have done, joint space. Okay, you see that in this Puma you have Q1 all the way to Q6, and each of them will be controlled by a processor and then interface, or rather the interface that get to the processor to control the joint, right? So each of these modules here is a QK, okay? Or maybe I should use I, QI. And eventually we want the robot to work in a task space. So what we can do, this part is the closed loop control. Maybe I should use a different color. Okay, so this part is a closed loop control. And in order to make sure that the robot is working correctly in the task space, in between there is a trajectory conversion. Okay, it actually goes through a trajectory conversion. So basically, this trajectory conversion is really the so-called inverse kinematics. Okay. Of course, it doesn't have to be analytical. It could be some numerical solver. Okay, that map your task space to your joint space. All right. So notice that this is just this feed forward. It doesn't actually change it. It is actually independent of the outcome that is being sensed on the robot. So it doesn't know what happened to the robot arm. This thing will just be sending some desired this motion, theta d, theta dot d, theta lambda dot d, without knowing, without reference to theta. Okay, the actual state of the robot. Okay. So there's a joint space and a task space. All right. So this is when we put the inverse kinematic outside our control loop. Okay, the first figure 10.10. This is outside the control loop. And so the computation is actually done, it can actually be done more or less offline, okay? Not really at the loop time, okay, at the update rate. But there's another way of computing within the control loop, okay? So let's say we just send in the desired so-called desired motion in the task space. In task space. Okay, so if we are sending desired motion in task space, within the loop, we will need to be able to solve. So in this part, it is not just, previously it's just gain, right? Now it is gain, okay, not just gains, but also coordinate conversion. Okay, so maybe I can make this a bit more illustrative. So now what is really the difference is the computational, whether it's done before the control loop or is it done within the control loop. So of course, figure 10.10 is before the control loop, okay? And then this figure 10.11 is within the control loop, okay? So one thing to note is that this part here, where you convert your theta, the joint state, to your task space state, this part here, it doesn't really have to be a mathematical operation. Okay, it's not necessarily a mathematical operation. It could be a sensor that directly sends your position in the task space. Okay, so maybe just make a very quick note. Okay, so this is not necessarily a mathematical operation. It could be direct sensing. Okay. So say, for example, if you have a robot arm, okay, so there are a few ways. If I want to know my X here, okay, this part here is, okay, this part here is X. And then of course I have theta. This part here is theta. The joint is, all these joint are thetas. Okay. If I put an encoder at the joint top, okay, if I put a sensor, then I will be measuring theta, and then I need to convert it to my X. But let's say if I have a camera that can track let's say this is a camera that can directly track the position here. Okay, then I can straight away get my X without having to do the mathematical operation. Okay, so now you can directly close the loop. Okay, you can close the loop by sensing in the task space instead of at the joint space. Okay, so for those who are working on robotics project, you will see that there are different situations. There are different situations where you might need to consider whether to do this Cartesian-based control scheme or this joint-based control scheme with Cartesian path input using trajectory conversion before the control loop. All right. So just a very quick exercise to kind of ask yourself if you to test your understanding of the concept when it comes to the application. Say if you are controlling this multi-joint snake robot, okay, which control scheme will you actually use? Or say you are trying to control this serial arm link, okay, which control scheme do you think is more appropriate? Right? I don't know if I can very quickly just put this maybe. Okay. I think there are only a few of you. You can take some time to think about this. Okay, as you go about, oh, I shouldn't have said this. Okay, I guess only one of you respond. But the idea here is that when we are putting in the whether we put the computation within the control loop or before the control loop will actually have a very serious implication. So in the case of a serial manipulator arm like this, okay, this is actually more suitable for the Cartesian-based control scheme. And then when we are talking about this multi-joint snake robot, okay, we don't really want to put it in this Cartesian-based control scheme, right? The idea is because, of course, there could be a few reasons, and sometimes there's no right or wrong in when we consider the practical condition. We have to evaluate a lot of factors. But in this simple case, you will see that for this two-arm manipulator, okay, it is okay to have this computation within the control loop, but when you have, say, 10 joints, okay, each time you have to wait for the entire updating of this control loop by solving the inverse kinematics. Okay, this coordinate conversion here is solving the inverse kinematics. All right. So I guess a lot of you get this correct. okay, based on the polling, you will see that you don't want to solve for inverse kinematics when you have so many. Sometimes you need to consider redundancy. So the conversion is actually not very straightforward. And in the control loop, if you have to wait for it to finish in order to execute the next cycle, okay, this is actually not going to be timely. Okay, so it will actually not work out that well. And of course, that another important reason is that you actually prefer to have your serial arm tooling manipulator to be this Cartesian-based control is because a very small error, okay, in your angle will actually cause a very large error in the task space, right? So maybe just maybe this is not so obvious. If you understand the idea of Jacobian, you will know that each of these joints are actually it is actually a weighted combination of influence of this joint that result in a task-based motion. Okay, so the task-based motion is actually a combination of all these joints, a weighted combination of all these joints. So if you have only two joints, a very small error, okay, say a small error in Q will actually lead to large error in X. So you don't want that to happen. The best thing is if you just put a sensor here and you measure Q, and after that you calculate this X, okay, it will actually result in a larger error than if you use a camera, for example, or any other tracking system, okay, a camera in this case, to get an X, it is actually giving you a more accurate measurement. So for this, it's actually more suitable using this Cartesian. But for a snake robot, each of this error here, Q, is going to have a smaller influence on your error in X, right? So that is the rationale or logic behind this. Okay. All right. So I'm glad. Yeah, most of you actually understood this concept quite well. Okay, so Cartesian control scheme, not just a conversion in your coordinates. Okay, just now what we have seen here is actually a conversion of coordinates. We send in X and then we want to change it to theta. So inside this thing, it actually changes to theta first. Okay, a few things. So it actually first convert to theta, and then it convert to pound. Okay. Oh, maybe I should. So the coordinate conversion, change it to theta, and then the gain, change it to tau. All right. So this is like gain. So this is just coordinate conversion. Okay, but we can choose which domain do we want to do our coordinate conversion. So in a case like this, okay, you can do it in your spatial domain, and you can also do it in your force domain. That means you can choose to change X to this, all right? Or you can choose to change false out. Okay, both of these are this coordinate conversion, but one is in the space and one is in the false domain. Okay, of course, this is obvious, which is false domain and which is space domain. So how you do this, of course, if you still recall what we learned in week 4, right? And also in week 3, where we start looking at Jacobian. Okay, so this part is just inverse of your Jacobian, and this part will be Jacobian transpose, right? If you ATF. Okay, so if I send in a false, I just multiply it by Jacobian transpose, I will get my power. Okay, and the same thing, yeah, I might need to solve for this inverse. Right? Because that is a definition of Jacobian, right? This is a definition of Jacobian. Okay. Okay, then we will move on to nonlinear control scheme. But I'm slightly running out of time, but we have one more lecture before the midterm test. So let me just very quickly wrap up on, okay, I guess maybe I will do this next week, since we might actually be doing in-person lecture next week. I'm not sure yet, but it seems to be possible. So I will leave this to next week. So next week, we're going to wrap up nonlinear system. Okay, how some of the strategy that we can use for nonlinear control. But what is really important is your control law partitioning. So now that you have understood this control law partitioning, later on, a lot of things will be quite straightforward and easy. Okay, so next Tuesday, we're going to look at nonlinear nonlinearity and also on force control. And after doing that, we will probably spend about 45 minutes for that. And the remaining time, we will do a very quick revision to prepare you for your midterm. All right. So midterm is on Thursday. Okay, I will give a short revision on Tuesday. Okay. So I will update you on the status of lecture, whether we are able to get back for in-person lecture. Okay, so probably if we are able to get back to in-person lecture, we will also start the lab next week. All right. So just a reminder for graduate student, okay, make sure that you submit your one-page abstracts soon, okay, on the Blackboard. All right, and homework 4 is available, so please check it out. All right, so that will be all for today, but I'll be around until 11:20. Okay, so if you have any problem, just go ahead and ask. Right, I will stop the sharing. I will stop the video recording.